Morning again, and I'd like to add my welcome to Madan's and hope you have been benefited to this last 2 days. And today we're going to look at the topics on the flow structures in supersonic nozzles in the morning, and then in the afternoon, in the morning itself, in the second part, we have an introduction to Schlieren measurements, and the afternoon you'll have a practical section on Schlieren imaging method. Okay, so we will start with the nozzles, flow structure in nozzles. Before that, I think we'll start with the shock interactions and reflections. We basically touched upon a little bit in yesterday's lectures. We are really going to look at what will happen when a shock wave intersects on a solid wall or a shock wave intersects a free boundary. So now what you can see is, now you see a concave structure. So concave, so here is the flow, it encounters a shock, concave one. Then we have the formation of an oblique shock. But what will happen when the flow is supersonic and then you have a convex surface? So that is what we see in the next part. So then we result in the formation of expansion fan. That's called Prandtl-Meyer expansion fan. So that's what you see here. So which is, we will be discussing a bit later on the expansion fan. This will be, there will be a head wave and then there will be a tail wave. So for example, if Mach number is equal to 1, the head wave is that. If the Mach number is greater than 1, and then accordingly, depending on the strength of the flow, you have this head wave. And then depending on how the flow has turned, then you have the tail wave. In between, there will be series of fan of expansion waves. We will come back to that later on. So now you can see from the convex surface, the flow just turns. If it's a concave surface, then the flow turns. Now, what will happen when an oblique shock encounters a solid boundary, solid wall? What will happen when an oblique shock encounters a free boundary? What will happen when an expansion fan encounters a free boundary? So these are the three cases which we are going to look at it at a global level, at the surface level, for us to just to know what will be happening there. That's what we'll be looking at it. So we discussed this yesterday on a flow over a wedge, a semi-wedge, half wedge. This is a phenomenon which is well known to you at the moment. If you have a full wedge, then probably for the same upcoming Mach numbers, for same M1, then you can have a symmetrical flow, but sort of a mirror image of opposite kind of family to the events that is happening here. Now, if the wedge is unsymmetrical, this is to picture about a different angle of attack. This angle here will not be the same as this angle here. So accordingly, the strength of the shock wave will also be different, and the flow turning and the angle, everything will be different. And yesterday we looked at the situation, what will happen if an oblique shock intersects a solid wall. Now we looked at the situation when a flow encounters an oblique shock, the flow will turn. If there is a solid wall there, if there is no intervention, the flow will go and hit the wall. So the oblique shock will be reflected before that, so that the flow that encounters oblique shock will turn exactly with the same angle, and then it will go parallel to the wall. Now, what will happen when two oblique shocks of opposite family? So here is one oblique shock and here is another oblique shock. Now what will happen? If they intersect, they will pass through. But the only thing is it will bend. It will not go exactly in the same line through which it was traveling, and that is what you see here. So the pink line, what you see here, the two oblique shocks which intersect, they pass through, and that's what you see in the orange one, but they bend. Okay, so they intersect, but then they bend. And from here you have a slipstream. Slipstream is just an imaginary, invisible path. There is no communication between this side and that side of the road. Because it is symmetrical, the properties are similar. But it becomes more complex if the strength of the oblique shock are different, and that is what you see here. If the strength of the oblique shock are not the same, they intersect and then they pass through, but still they bend. That is there. Then the slip line is at an inclination, and then only the pressure and the flow angles are similar. Rest of the properties are different. They don't mingle with each other, they just go past. But the key thing for us to know at this moment is that when two oblique shocks meet, they pass through, then they pass through but they bend. What will happen if we have a shock interactions of same family? For example, if we have a very sharp concave surface, then you have one strong oblique shock. But if it is not a strong concave surface, so for example it is gradually turning, then you will have the initiation of the weak oblique shock, and have a weak oblique shock and a weak oblique shock. Now these weak oblique shocks are of the same family. They coalesce and then they form a strong oblique shock. So the flow that comes over here that encounters this oblique shock will turn, and those flows that are coming over closer to the wall, they gradually turn, then they go parallel. So what we need to know at this moment is that when we have shock interactions of the same family, they result in the formation of the weak. You have shocks coming from the same family, they coalesce. That's the main thing. Shocks coming from the same family, they coalesce, and then they form a strong oblique shock. Now what will happen if there is a convex surface? As I did mention, when you have a convex surface, then you end up in forming a head wave. That head wave position is adjusted according to the upcoming Mach number. So if it is hypothetical 1, m equal to 1, the head wave is vertical. It starts here. Okay, so if the Mach number is greater, then the head wave position turns. Unlike shock waves, which are not isentropic. Expansion fans are isentropic, so you can treat them with the isentropic solutions. So it is much easier in that sense. Then, depending on the angle of inflation, this is theta w is the wall turning angle, then the tail wave will be positioned in such a way that you can have the flow gradually turned. There are a number of expansion fans, numerous expansion fans, through which the flow gradually turns, and then so this is an expansion process. So the Mach number of the flow leaving this tail wave will be greater than the Mach number of flow that is meeting the head wave. This theta w is the wall turning angle, and that is the difference of the Prandtl-Meyer expansion angle. So Prandtl-Meyer is defined as mu. So nu of m square root of gamma plus 1 by gamma minus 1 tan inverse of square root of gamma minus 1 by gamma plus 1. You don't need to remember this. This information is also given in the table. In the table you find this value. You can see that before, you can see that new value there. So that's the Prandtl-Meyer angle. Okay, so when you have a concave surface, we have the formation of the oblique shock, strong oblique shock. When you have a convex surface, then the flow turns to the expansion fan. Expansion fans isentropic, but the shock waves are non-isentropic. Now, what will happen if you have an oblique shock wave? Now, this green line, what you see here is the free boundary. It's like a jet. It's not a solid boundary there. So when an oblique shock encounters a free boundary, you end up in forming an unlike reflection. That's what we need to know. So unlike reflection in the sense, an oblique shock will result in forming an expansion fan. So what we see here is that the flow that comes in encountering an oblique shock will turn, and then that encounters an expansion fan will turn slowly, and then it goes parallel to the surface, the free boundary. So this is an unlike reflection. So whenever an oblique shock encounters a free boundary, we have an unlike reflection. So if it's oblique shock, then it ends in an expansion fan. Now similarly, when we have an expansion fan, so what you see here, this is an expansion fan. Prandtl-Meyer expansion fan of waves. So when an expansion fan, Prandtl-Meyer expansion of fans, encounter a free boundary, then you have an unlike reflection. For each expansion fan, you result in formation of a weak oblique shock of unlike reflection. So it's an expansion fan intersecting a free boundary. Each expansion fan will reflect an opposite kind, which will be a weak oblique shock. So there will be a number of weak oblique shocks. Weak oblique shocks will coalesce to form a strong oblique shock. So the principle of flow turning is very similar, like what we have discussed below. Okay, so I just wanted to go through because we need this understanding when we are looking at the nozzles. Now, so before we start, I think let's look at some of the basic stuff what we know. So when we have a subsonic flow entering a convergent geometry in this direction, in the flow direction, the velocity will increase and the pressure decreases. This is known to us. When a subsonic flow enters into a diverging geometry in the flow direction, the velocity decreases and the pressure increases. So we know also that when a supersonic flow enters into a convergent geometry in the flow direction, the velocity decreases and the pressure increases. In a similar way, when a supersonic flow encounters a diverging geometry in the flow direction, the velocity will continue to increase and the pressure will decrease. So this is known to us, and we are going to use this concept for extending our understanding of the flow in nozzles. So for example, when we look at a ramjet engine, so here is the inlet, here is the combustor. So again, you see, if you're trying to zoom into this part of it, you can see that this is the convergent divergent geometry. Again, this is the inlet part is convergent divergent one. So we already looked into this, we already looked into it. Now today going to look into the nozzle part of it. So now you can see that the flow that is entering in a ramjet, here the combustion takes place under subsonic conditions. So m less than 1, the flow is going to accelerate, reach m equal to 1 at the throat, and then go for supersonic conditions here. So if we can try to imagine the way that we can look at it is as a subsonic flow enters into a convergent geometry, accelerates and reaches m equal to 1 at the throat, and then it continues to accelerate to supersonic speeds. So that is what we're going to look at it today as the convergent divergent nozzle. Before we actually start, let's try and understand some basic fundamentals which is known to most of us at the moment. Today you're going to have experiments, so I thought I will do an experiment here. Okay, so let's say that we have a nozzle which is connected to vacuum, and this, we don't want the vacuum to be filled all through. Let's put a valve here. Okay, and this valve we can control, we can vary the position of the valve here, and let's connect it to the reservoir here. This is upstream side is connected to the reservoir, so there's a pressure in the reservoir, temperature in the reservoir, and density in the reservoir. So this is an experimental setup here. This is the place where we're going to measure the pressure at the exit, and here is the pressure outside, ambient pressure P0. Now pressure, exit pressure, and P naught. The exit pressure most of the time will be equal to the ambient pressure, but not always. Not always, but it will be equal to the ambient pressure. So let's try and do this experiment, and let's try and monitor how the pressure distribution is happening here. So on the y-axis, we are going to plot P, the pressure at any point, divided by normalizing it with the reservoir pressure. Now initially, let's start the experiment. Let's take the background data. 1, valve is closed. The pressure is uniform throughout. There is no flow. So we are having a background check. Our sensors are reading that thing is happening here. That's true. It's working well. Now we're going to start the experiments. I'm going to just open the valve. Open the valve. So we are having P naught less than the upstream pressure. We create a pressure gradient. Now here you can see that exit pressure is equal to P naught. Exit pressure is equal to P naught. We just open the valve. We create, exposing it to vacuum. The ambient pressure is dropped. The exit pressure also feels the same thing. So P equal to P naught. You create a gradient. This gradient will cause the flow to enter in. The flow will start to accelerate as it comes into the convergent geometry. Now we know that subsonic flow, the flow is still subsonic. Now as it flows into the subsonic flow, the pressure decreases and the velocity increases. Now, for example, let's say this is only Mach 0.3 at the throat. Still subsonic flow. So this is the pressure increases in the divergent part. Now we will repeat this one. We will open the valve further. The ambient pressure decreases further, and then that is also equivalent to the exit pressure. Now the gradient is becoming a bit more. The flow starts to accelerate even much faster. So the velocity increases, and it increases, but still not m equal to 1. Let's say for a purpose it is 0.7. So the flow entering the diverging section is still a subsonic conditions. So the pressure increases. Point. Now let's continue to work on this experiments further. We are opening the valve further. The ambient pressure decreases. The ambient pressure is same as the exit pressure. Gradients is much stronger. The flow is now accelerating much faster, and then it reaches a value of m equal to 1 at the throat. Once it reaches m equal to 1 at the throat, then there are two possible solutions for it to happen as it passes through the divergent section. Either it can have a subsonic solution, or it can have a supersonic solution. Whether it will have a subsonic or supersonic solution will depend on the exit pressure. Now, if the exit pressure is higher, then we will have a subsonic solution here. At the same time, if we drop the exit pressure to 5, then what we'll have is the flow that expands in the nozzle will continue to expand and have a supersonic solution. So now here up to this particular point, from here to here, m is less than 1, subsonic solution. Here also exit pressure is equal to P naught, and here m is greater than 1. Now I'm going to drop the pressure below the condition 5. So when I'm trying to do that, the flow will expand isentropically through the convergent part, and the flow will expand isentropically also into the divergent part. And then it comes to the point of the exit and realizes that, oh, the pressure is not 5, it is 6. So the flow expands through Prandtl-Meyer expansion fan to reach the pressure. So here what you see here, the exit pressure is greater than P naught, which means it is under expanded. When PE is equal to P naught, it is perfectly expanded situation. Now let's continue to do this experiments. Let's say this is the point here, 7. Now the flow will expand isentropically to the convergent part, and then it will also expand isentropically in the divergent part, and the flow will realize that the pressure at the exit is much higher than the pressure at any point. So here what you see here, the P is equal to less than P exit pressure. So then the flow will realize that it has to go to that place. So the only way through which the flow can jump is through the formation of normal shock. Once the flow encounters a normal shock, the flow becomes subsonic. Then a subsonic flow will enter into a divergent geometry, then the pressure will increase. Now let's drop the pressure even further here, 8. So the flow expands isentropically and then expands isentropically, and it has overexpanded. So now you can see the situation where from here to here the flow has overexpanded. It has overexpanded. It realizes that it has to go up. So the only way is to encounter a normal shock. The flow jumps. Now let's repeat this experiment further, and let's say that this is the pressure 9. So the flow starts to go through an isentropic expansion in the convergent part and the divergent part, and it comes to the point and realizes that the exit pressure is not very high compared to the position where it is. So the easiest way for it is to an oblique shock to reach this value. So now you can see that when we try to operate a nozzle, we can go through different modes of operation. You can have a perfectly expanded mode of operation, you can have an overexpanded mode of operation and underexpanded mode of operation. Okay, so this is the place where it gets choked. So maybe you can put here P star by P R. All of you understood this one. This is the basic background of it. Let us consider a situation here. You have a convergent divergent nozzle. The pressure here at this point is less than the ambient pressure. Now, what is the situation when pressure is less than the ambient pressure? Sorry, this is the ambient pressure. Pressure less than ambient pressure here. So it is overexpanded. So this is an overexpanded situation here. Now, the flow comes to the exit, and now it is realizing that it has expanded more than the ambient. Then the flow realizes that there is only one way to which the flow can balance, the pressure can be balanced, is through the formation of an oblique shock. An oblique shock will form at the exit of the nozzle. And there will also be an oblique shock form. So when two oblique shocks of opposite family, they meet, they pass through, but then they don't go in the same line, they bend. They bend. But before that, what actually will happen is the flow will can you see this one? This is what is happening here. The flow oblique shock will come because the flow has overexpanded. Then the oblique shock will intersect. They'll pass through, but they will bend. Okay. Now the flow will turn into, and then we see the following things happening here. Now, when a flow encounters an oblique shock, the static pressure will increase. So the pressure at this point P will be equal to P naught. The pressure at this point will be equal to P naught. Now again, the flow will encounter an oblique shock. The pressure will increase. So P will be greater than P naught. The pressure will be greater than P naught. When the pressure is greater than P naught, then you end up in the formation of an expansion fan. You end up in the formation of an expansion fan. When the flow encounters an expansion fan, you end up in a concave surface. So what will happen to the flow? The flow will turn. So here you can see the flow will turn. the flow will turn. Now you see that you have an expansion fan encountering the free boundary here. This is what you see here. Then before that, we can now write here from, so let us call this is at this, from here you can see that, okay, let's put an arrow here for you to understand. So now you can see that from here, the flow will expand. So pressure will be equal to P naught, P equal to P naught. Flow is expanding, okay? Then the flow will continue to expand as it passes through. Then P will be less than P naught. Now, what we see here again, at the intersection point, interactions will taking place here. A fan interacting with the free boundary will result in an unlike reflection. Number of unlike reflections will lead to an oblique shock of same family generating there, coalescing to form a strong oblique shock. Strong oblique shock. This oblique shocks will intersect, and they will not go in the same line, but they will bend. That bending depends on the flow conditions, the complex phenomena here. So what we see here, the free boundary flow will turn because of the oblique shock, will cause the flow to turn. Now again the pressures will be, pressure will increase, pressure will be higher, and the pressure will be greater than P naught. Because of that pressure greater, we end up in the formation of and similarly we end up in the formation of expansion fan. This will cause the flow turn. Then this will end up in the intersection of it. Then you have the formation of the intersection of unlike reflection, weak oblique shocks, they'll meet coalesce to form a strong oblique shock. So here again, we see the pressure will be equal to P naught. The pressure will expand, P will be equal to P naught. It will expand, P will be less than P naught. Then the flow jumps. And then, so this process continues until there is energy left for this process to continue. So this is what we call as shock diamond, the structure. This happens for an overexpanded nozzle. Now let's look at the situation where we have an underexpanded situation where underexpanded situation So if it's under expanded, P is greater than P naught. That is the condition here. When the situation is P is greater than P naught, we end up in the formation of expansion waves right at the start. Expansion waves. So here we see an expansion fan at the start here. So when you have an expansion fan, you see the flow will turn. Basically, the flow turns. Flow turns. And we end up in a situation where the fan will be interacting with the free boundary, and then we end up in a formation of an unlike reflection of forming an oblique shocks which are of weak in strength. So the weak oblique shocks will be an unlike reflection. They coalesce to form a strong oblique shock. So in the process, we see that when the flow expands from the nozzle exit, so then the pressure will be equal to P naught. Pressure will be equal to P naught. It expands further, P will be less than P naught. That's also one of the reasons why we have this oblique shock here. Now, because the flow has encountered an oblique shock, the flow will turn. At the same time, the shocks that intersect will pass through, but it will not pass through in the same line. It will bend once a shock wave, oblique shock, intersects with a free boundary, then you have an unlike reflection. And this will cause the flow to turn further. Flow turn further. So this phenomena starts, cycle repeats. Now here, as the flow jumps, the pressure will increase to P naught. The pressure will increase to P naught. And then again, pressure will increase, then it will be greater than P naught. Then the expansion fan comes. The pressure will be equal to P naught here. Pressure will be equal to P naught. And then pressure will be less than P naught. Then you see the flow again intersecting to form an unlike reflection, form a weak oblique shock, which coalesces to form a strong oblique shock. And then the flow turns. So this process continues until there is energy. So these structures, what you see here, are called the shock diamonds. Shock diamonds will occur only when the flow is either under-expanded or over-expanded. When you have a perfectly expanded situation, you will not have any shock diamonds that is being formed there. So this phenomena, what you see here, I think, so here is, if I represent this on a very fundamental level. So if this is the pressure of the reservoir in this experiment, pressure of the reservoir, and then it expands to the ambient pressure. In the process, the flow gets choked. P star, I'm looking at a simple case, isentropic situation here. Sometimes the pressure, exit pressure can be here, which means where C is, exit pressure is greater than P naught, which is under expanded, which hasn't expanded. Sometimes you can have a situation PE is less than P naught, which is over expanded. Okay, so we have done enough problems with the shock waves. So when we have flow encountering an oblique shock, the flow turns into it. Now, when we have a flow encountering an expansion fan, the flow turns in this direction here. Okay. Okay, so let's finish this morning section, the first part of it, by working out a problem. Problem you see in 9, problem sheet, problem number 9. A military trainee aircraft have been fixed with a fixed geometry, convergent, divergent, and nozzle, which experience an under-expanded mode of operation, which means P is greater than P naught. The gases leaves the nozzle exit. So let's say here, leaving it, let me put this in 1.6. It is leaving the exit at 1.6. This corresponding static pressure here at the exit is 185 kilopascal. If the ambient pressure outside P2 is 96 kilopascal, calculate the angle through which gas jet disperses immediately after leaving the nozzle exit. Now, since we have a situation where the flow is under-expanded, we result in the formation of an expansion fan. When you have an expansion fan, the net effect, what you see here, is the flow will turn. The flow will turn. So this will be the free boundary flow dispersion one. The jet will disperse like that, flow turn. We are asked to calculate what is this angle. What is this angle? Calculate the angle through which the gas jet disperses immediately after leaving the one. So a couple of things for us to. So when the flow expands, Mach number M2 will be greater than M1. The flow downstream Mach number will be greater than. Since it is expanding, we know that the pressure P2 is 96 kilopascal. It is lower than what we have here. Okay. The way to determine this is to use this Prandtl-Meyer. This is basically the flow turning angle is Prandtl-Meyer expansion at M2 minus Prandtl-Meyer expansion angle at M1. So we saw this morning that Prandtl-Meyer expansion is square root of gamma plus 1 by gamma minus 1. We have tan inverse of square root of gamma minus 1 by gamma plus 1 into m square minus 1. And then we have tan inverse of square root of m square minus 1. So this is the okay, so here's this one. Yeah. So this is the Prandtl-Meyer expansion 1, the equation what I've written there. Okay, so here is the Prandtl-Meyer one. You don't need to know, or at least for this course, you don't need to memorize anything, but you don't need to know this thing. But we need to know how to use this equation. That's what it is, through the tables. From the information that is given, we have M1 is known, which is given here. Since it is a Prandtl-Meyer expansion, the expansion process, let's say here, if it is P, okay, let's if this is expansion 1, so this is PT1. So this pressure P1 is given as 185. The static pressure is given here. Static pressure is given here. The corresponding stagnation pressure at this point is PT1. So this is what you see here, PT1. And now we know the relationship between PT1 and P1, which is equal to 1 plus gamma minus 1 by 2 M1 square power gamma by gamma minus 1. And this M1 information is given here. Okay. So we know this M1, we know gamma is 1.4, and we know P1, 185 kilopascal. So we can find PT1. This is unknown, which we can find it, PT1. Now, similarly, what we have here is the pressure at the exit is P2. Now, the beauty here is that it is an expanding isentropically, so there is no losses there. So this is again from here to here is, if there is losses, then we will have the generation of entropy. If there is no losses here, then if it is losses, if there are losses there, then somewhere here we will have this one here. PT2. Since there are no losses in the system, so PT2 also lies exactly the same point because of there is no losses system, isentropically expanding in this expansion fan. So we can still write here PT2 by P2 is equal to 1 plus gamma minus 1 by 2 M2 square, or gamma by gamma minus 1. Now P2 is known given the problem. P2 is given as 96 kilopascal. M2 is not known. P2 is known because we can find PT1 here. PT1 is equal to PT2. Okay, so if we can find, if this is also known, then we can find M2. So M2 will be nothing but PT2 by P2 power gamma minus 1 by gamma minus 1 into 2 divided by gamma minus 1 square root of it. So this is M2. So now you can see that M1 is already known and M2 is now we can get from this equation. So now M2 is also known. Then we can use the tables to find what's the angle through which the flow has turned. Is that clear? Okay, so let's work out this problem. Now directly use the table and tell me what's the value for this one, Prandtl-Meyer angle. 14.861. This value of M1 is 1.6. Go to the table 1.6 and then directly take the value there, mu. What is the value for M2 now? Or let's say what's the value for PT1? Tell me what's the value for PT1. 7, 8, 32 kilopascal. So PT2 is equal to PT1, and then just rearrange this, find the value for M2. 2.03. 2.03. So once you have got the value, find the Prandtl-Meyer for M2, which is 2.03. 27.20. So what is the flow turning angle? How much? 12.34 is the angle through which now we can see this is 12.34 degrees, the angle through which the flow has turned. Is that clear for all of you? Yeah. Now let's finally summarize everything. So this is what we have just covered. Looked at the experiments there. Situations where you have an oblique shock and you have the normal shock also possible. When it is perfectly expanded, you will not get any shock waves. This is the situation here, perfectly expanded one. So when it is overexpanded, this is the regime you're looking at, overexpanded, and this is the underexpanded regime. This is the one. Now this is what you see there. in an aircraft, behind an aircraft, you see the structures there. These are the structures now you have drawn by yourself, the shock diamond structures. So you see the shock diamond structures here, shock diamonds. You see this in the nozzles of the missile or aircraft. And this is SR-71 Blackbird. We'll touch upon these things in the day after tomorrow. But now, this afternoon, Dr. Madan will be generating this sort of shock diamonds, and then one of the best techniques and tools to study this shock diamonds is Schlieren imaging. And that's what is going to happen this